Okay, so we'll work for about a half an hour here, and I'll go through the definitions, and we'll kind of do something interactive. Thank you all for putting on your dot cam so I can see you. And I'll ask you to, every now and then, put an answer in the chat and go from there. So far, we've been using this definition right here, kind of, like this one. The number of outcomes in the event E is the top number, and then the number of possible outcomes is the bottom number. So there's another, particularly in statistics, where we collect data and we infer the data that we collect to some bigger group, like all Americans or all college students or something like that. And if a probability that we're going to be calculating is based on data, then we call it an empirical probability. But it's a simple fraction like this, but it looks a little different. We use different words. You can see it's kind of the same. So an empirical probability, and I think our author calls it an experimental probability, as if you're doing an experiment of some sort. The number of times, observed number of times E occurs. So some kind of category, and how many times, the frequencies, we're counting up individuals in a poll or something like that, divided by the total number of observed occurrences. And we call this in statistics the sample size. So lots of probabilities are calculated, and if you go on to take statistics, you're going to be doing the same sort of stuff. So let me show you what this would look like. Here's an example, and you can see in this table that it gives the ages of 3,000 American moviegoers. So just imagine that on a random day, they went in and they asked, in all of the different theaters across the country, they asked them their age. And they reported their age, and then they put them into these groups. And they were only interested in children 12 or older. So they created these categories. You've got the younger age, the ages 12 to 24. You've got the next age group, 25 to 44, and then the 45 to 64 crowd, and then the 65 to 74. So usually they break it off at 65 because that's where we start talking about seniors. And before 65, we have mostly working people. And those two groups are quite different in a lot of ways. Now, they said that they had 3,000 moviegoers. So we should probably, let me get this light going here. We should probably add those up just to make sure. Yes, 3,000. They add up to 3,000. Okay. So the 3,000 were the individuals that were asked. So that becomes the total number of observed occurrences. You know, they can't have a formula for every single context. So you'll have to infer that the total number of observed occurrences would be the total number of, in this case, those who were asked. And so our denominator is going to be 3,000 for all of the problems in this section, because that's how many were asked. So then they're going to ask us probabilities based on this. What is the probability that a randomly selected moviegoer, think that someone's reaching in the hat and pulling up 3,000 names, what's the probability that the moviegoer is less than 25? And so according to our probability up here, we have to ask the question, well, how many of those people are under 25? Because that is our event. It's like our event divided by the total number possible. So how many are less than? There's 25. Less than 25 would be these folks, and there are 900 of them. So we have 900 that are age less than 25, and we divide that by the total number asked, and you either write that as a fraction or we write it as a decimal. Now, normally when we have empirical probabilities like this, it's more meaningful if we use percentages, because we're very familiar if we say something like 10% of moviegoers are under 25 years old. We kind of get a sense of what that means. We'll take 900 and divide by 30, 3,000 I mean, and at the same time I'll convert that to a fraction. All right, so it's 3/10. As a decimal, 0.3. As a percentage, 30%. So it asked for the probability. So these Either these two, they're both equivalent. One's the fraction form of the number, the other one's the decimal fraction form of the number. Either of those would be fine. Now, if they ask you to interpret the probability, that's when you would bring in the percentage. So 30% of the moviegoers are less than 25. Yeah, I think you're good. I see all the same answers, 0.64, and I believe that's correct. But it's between 25 and 64, so we have to add both of those. Again, either one of those two answers would be correct. And the last one, the probability that a randomly selected moviegoer is older than 44. Here's 44. Older than 44 would include those two. So you would have to add those two classes and divide by 30. It looks like 0.34. And that's 17 out of 50. So when you're doing problems, just be sure that you know the form of the number that they want, either the decimal or the fraction. You know, this one's easy to convert to a percentage, this one's easy to convert to a percentage, and this one's easy to convert to a percentage. Fractions, not so much. All right, so expect to see some tables like this for these empirical probabilities in your homework as well. We will get to some two-way tables in a second, and those are a little trickier to read. All right, when we did the sets, and this begins section 5.1.4, we looked at unions and intersections, and we've got the analogy to this in probabilities as well. And so let's just start off with an example, then I'll give you the general rule. You'll see that it's very similar to what we had in sets, and then we'll look at a couple of problems using this addition rule. And it's an addition rule to calculate a specific probability. And the probability that we're going to calculate is the probability of E or F. So you will see in the formula that it involves an addition sign, and that's why it's called the addition rule. But the addition rule is not helpful if you wanted to calculate the probability of E and F. It's only a probability of E or F. And remember that that's the same thing as the probability of E union F. So union and or go together. Okay, so we have 1, 2, 3, 4, 5, 6 students that are taking classes in statistics or writing. And you can see Matt here is in the middle. So Matt's taking both statistics and a writing class. Pamela and Sam are taking statistics, but not taking a writing class. And Nandini, Elliot, and Jill are all taking a writing class, but not taking the statistics class. And then they pose a question. If we were to select one friend at random, take each of those 6 names, draw one out of the hat, what's the probability that they would be in either? So either means or. And you can even see there, statistics or writing. So let me abbreviate statistics with an S and writing with a W. So what is the probability, P, capital P, that they would be in either statistics or writing? So you can see it's calculating a probability with an or in there. Now from our work on the sets, right, you know A or B means all of those individuals in A or in B or in both. Oh, but this one says, but not both. So how many, all right, so the bottom number is 6 because it's like we're randomly selecting from the 6. How many of those students are taking statistics or writing, but not both? So I'd have to alter that slightly. Yeah, that's right, 5, 6. One or the other, but not both. Only Matt would be in both, so Matt would be excluded in the group. Let me put some out to the side there. What's the probability that a student is taking statistics? What's the probability that the student is taking, a randomly selected student is taking writing? What's the probability that a randomly selected student is taking both? And that's where and comes in. And is related to our set operator intersection. All right, start with the first one. Probability that someone's taking statistics. Of all those answers, I don't see a correct one yet. Okay, probability that someone is taking statistics would be the observed number of students taking statistics. How many students are taking statistics? 3. How many total students? 6. So 1/2. So I didn't say this. I didn't say what's the probability that somebody is taking statistics but not writing. I didn't include the but not writing piece. So these 3 individuals, would you agree, are taking statistics? Some may be taking other courses. Others might not be taking other courses. But these 3 are definitely taking statistics. They could be in a statistics class together, in fact. Okay, with that understanding, what's the probability that someone's taking writing? Okay, good. 4 out of the 6. And some of you even reduced it. What about, what's the likelihood that we would randomly select a student and that student happened to be taking both writing and? Okay, good. There's just 1 student in there out of the 6. All right, now, one last one. What's the probability that a student is taking not and, but or? Statistics or writing. And that's the inclusive or, so that means that we're looking at all students who are taking either one of those courses or both of those courses. So if we took and did S union W, then we would shade this whole area here. It's the union. So it's kind of the same idea. So inside this whole grouping, we count them up, 1, 2, 3, 4, 5, 6. So the top number is 6, but the bottom number is also 6. So we don't have any students outside the circle, so it doesn't increase our denominator at all. All right, I wanted to do this example because now we can illustrate the addition rule. And notice right there is the addition piece of it. And it says this. Now, our events are not A and B as is listed here in this general format, but the idea is the same. Now, if we change that generic formula with A's and B's into an analogous formula with S's and W's, you could alter it and write it this way as well. Sometimes you'll see it with E's and F's, and you'll see it all lots of different places. But we calculated each one of these, and I want to show you that this relationship holds. And then I want to show you a Venn diagram representation of it. Or W, that was 1. Probability of S, that was, you know what, I'm going to write these as, I'm going to write these with the denominator 6, so they're easier to add together. Plus the probability of W, 4/6, minus is in the formula, 1/6. And you can see that that statement I just wrote down is numerically correct. That is, if you take 3/6 and 4/6, you'll get 7/6. And then if you subtract 1/6, you'll get 6/6. And 6/6 is equal to 1. So the formula works out here. Now, the beauty of this formula here then is that if you can remember it, then a lot of problems will give you 3 of these 4. And if you have 3 of these 4 missing fractions, then you can find the missing 4th. All right, here's how the formula works. We know that the probability of A union B shaded is all of this. And, you know, let me just put some numbers in there, just so you have it in there. Let's say that this region is 0.2, and this one is 0.1, and this one is 0.4, and this one is 0.3. We have to have all 4 of those regions add up to 1. So the probability of A or B would be, just like we had with sets, we would add up all the numbers in those 3 regions in the middle, these here. So we would add them together, 0.3 and 4 is 0.7. Now let me do it another way. I'm going to add the probability of A with the probability of B. Why don't we just stop there and say this is the formula? Because if we did, then this is what would happen. If you take the probability of A, that's all of this, and that's equal to 0.3. You have to add those 2 numbers together. Then, if you took the probability of B, that would be all of this, all of B. And so you'd have to add the 0.4 and the 0.1 together, and that's 0.5. Now on the Venn diagram, you can see that that middle area, I shaded twice. I shaded it with both red, and I shaded it with green. So I added that middle region, 0.1, I added it twice. and I wasn't supposed to add it twice. And so what I'm going to do is I'm going to subtract out one copy of it. I'm going to subtract out the probability of A and B. And this is just so we don't double count the middle region. That's all that means. And that middle region is 0.1. And if you add those together, you get the 0.7. So if you just took the probability of A plus the probability of B, then you would get something too large. It wouldn't work out to the same. There it is. So there's the Venn diagram representation of the addition rule. Okay, number 13, I think this was from your Newton materials. You might run into this example. A group of friends take classes at the university in biology, chemistry, and physics, science class, and then you calculate the probabilities. And we have the probability of B is equal to 1/3. The probability of C, okay, so B is biology, C is chemistry, is equal to 1/2, and the probability of physics is equal to 1/6. Okay, so only biology, only chemistry, and only physics. And then the last one, a student takes both biology and physics with a probability of 1/4. So the way we write that would be biology, and then you can see it, and physics is equal to 1/4. So you're given a lot of information, and they wrote it out in words, and they wrote it in symbols as well. Now we have 3 sets here, so we're not going to be able to draw a Venn diagram with just 2 circles in it. So let's see what they want. What is the probability that a randomly chosen friend takes biology or physics? So if you could, map the B and the PH onto the A and the B. So instead of memorizing these as formulas, just think about the Venn diagram. The probability of A or B goes on the left-hand side. And then you have the probability of the first event, A, plus the probability of the second event, B, and then you're going to subtract off the probability of the intersection between those first two. So while they did give us this information about chemistry in this problem, it turns out that we're not going to use that little clue about chemistry, that the probability that one of your friends would take chemistry is 1/2. Probability of B, or you just kind of use the formula, probability of the first event by itself plus the probability of the second event by itself, and then you're going to minus the probability of the intersection. And that would be those individuals taking both biology and physics together. Well, it takes a while, but they've given you all the numbers they've given you 3 numbers of the 4 that you need to find that missing 4th, because the probability of B was given to be 1/3, plus the probability of, what we're doing here is substituting. We're substituting our mathematical notation for numbers so that we can calculate something. The probability of physics is 1/6, and then we're going to subtract out the probability of biology and physics, and that's 1/4. Once you evaluate this, and if you want, you can get the common denominator of 12 and add them all together, or you can just say 1 divided by 3 plus 1 divided by 6 minus 1 divided by 4, convert to a fraction, and it turns out that it's, you might not recognize this, but 1/3 plus 1/6 is equal to 1/2, and 1/2 minus 1/4 is 1/4. So you have a collection of problems like this. All right. Why don't you try number 14? And if you get number 14 done, then try to draw a Venn diagram that models this problem. The more ways that you can think about a probability, the more likelihood that you're going to get it right, because you have more than just one tool. You don't have just the formula, you have the Venn diagram as well, which is another tool. A is the shift from 8 a.m. to noon, 4-hour shift, it looks like. B represents the shift between the hours of 12 and 4, another 4-hour shift. If the shifts are assigned with the following probabilities, it's a probability that someone would be assigned both shifts at a lot of 0.18. Okay, let's take a look. we have the probability of A or B is equal to the probability of A plus the probability of B. Now, when you're doing these problems, you're just going to need to remember that, hey, these formulas are tools that I can use to solve some of these problems. There are other things that you can do as well to solve these problems, but having a list of formulas that I won't make you memorize can be very useful. They're actually one thing that you can use. But they didn't give us these three numbers this time. They gave us different numbers. They gave us the probability of A is 0.28. The probability of B is 0.83. And then we need to subtract something here. And they gave us the probability of A or B. They gave us the number over here was 0.93. And then they asked us to find this missing number here. And these two add up to 1.11? Is it 1.11? 17? Yeah, 1.11. Yeah, so however you want to do this, if you, you can just say, what do I have to subtract from 1.11? But there are other ways to do it. And you could subtract 0.11 from both sides and get this. That's the addition formula. I said maybe to write down a Venn diagram. And for this one, here's A, here's B. And the way this would look is that A and B in here would be 0.18. There's not going to be anything outside the circle on the, you know, when you use this. Can you do this? Probability of A is 0.28. Remember those survey problems where you had to subtract? Same idea here. So 0.10 would have to go out here so that when you add those two numbers together, you get 0.28. And the probability of B is 0.83. So that must mean we have to put 0.65 out here so that those two numbers add up to. We know 0.18 goes in the middle because that's what we calculated here. And if the probability of B is 0.83, then those two numbers have to add to 0.83. So you'd take 0.83 minus the 0.18, similar to what you did with those survey problems to find that missing number. And then if you took the probability of A or B, then that would just require that you add those three numbers together and then guess what that is, what they told us it is up here. All right, let's try one other problem before break. And I mentioned that for these empirical probabilities, it's nice to have just a single frequency table like this, but sometimes you have a two-way table. So let's take a look at how you would interpret the two-way table, probabilities in the two-way table. I could take you through this example, but because it's a lot of OR probabilities, but I think that to apply the formula to problems like this, where you actually have all the cards right out in front of you, is probably a waste of time. Okay, what sort of education do Americans have? This is based on well, I'm not sure when the study was done, but you can see that they waited until the Americans turned 25 years old. So they only ask individuals that turn 25 years old because that would give them time to earn a degree, maybe multiple degrees. And so you can see that this number right down here, 174, is coded in millions. So this really means 174 million Americans are 25 years of age or older. And so then they asked them two questions. Well, they probably didn't ask them what their gender was but if they were filling out a form, then they would have to specify male or female. And then it looked at different levels of educational attainment. Less than 4 years of high school, didn't finish high school. Got the high school diploma, but didn't go beyond that. Took some college, maybe started, but didn't get a degree. Or this could be earned a degree, but maybe an associate's degree. And then their next category is 4 years of college or more. So it's talking about the number of years as opposed to degrees, I think, achieved. So, you know, keep that in mind. We have 14 million. And since this is, these would be individuals who are male, but these would also be individuals with less than 4 years of high school. So there's two different features going here. Amount of college or amount of school, and then gender over here. They're starting to ask a lot of questions now and add a question about transgender. And so a lot of times they will just point out that, you know, they're, for example, I was looking at the death penalty the other day and looking at the gender of those who were killed by the state in the country. And they broke them down by males and females, but then at the end they would say, in this list, there are 7 transgendered individuals. So at least they're reporting it out. Okay, how about if we do this? We will call males M and females F. And then for the years of education, I'm just going to classify them from A to B, or A, B, C, and D. So D is the highest level of years of taking courses. Now, before we get to the questions 42, 44, and 46, let me ask you this. What's the probability if we randomly selected an individual in this group that they would be male? The total in our sample is 174. That's going to be the bottom number. Of all 174 million, how many are male? These are male. Didn't have much high school. These folks are males. These folks are males. These folks are males. Oh, the total number of males is over here. So when they ask the probability that someone is a male, we would say 82 divided by 174. Now, it's very important when you're doing problems like this that you do not leave it in fraction form, because the fraction is essentially useless. Divide it out, take 82 divided by 174, and you're going to get the decimal. And I will round it to 3 decimal places, because if you round the decimal to 3 decimal places, then you can round the percent to 1 decimal place. And that's usually enough accuracy. Does that make sense? About 47% are male, about half, right? 47 is close to 50%. What's the probability that someone got their high school diploma and didn't go on beyond that? Okay, so good. You're focusing on both of these groups here. When you add them together, you get 56. These are the males that got a high school diploma only, and these are the females that got the high school diploma. So this says B just got a high school diploma without any indication of whether they were males or females. So yeah, you take the total number of Bs right down there, you have a column total. And then you divide it by the total in our sample, and then round to the nearest 3 decimal places. And I get 0.322. And we would say 32.2%. What's the probability that we would randomly select a person 25 years or older in the United States, and they were females that had 4 years of college or more? And 4 years of college or more would be D, and female. So females who earned more than, took more than 4 years of college. Now, because of the word, okay, I see some answers in there, 32, although that's to the other one. I see one answer. Looks like 12.6, couple of those. Yeah, so in this case, because of the word and, the individuals we're selecting, we want to make sure that they're both of those things. So they are both females and they've taken 4 years of college or more. So we're only talking about those 22 million females with 4 more years of college. We're not talking about males, and we're not talking about anybody who finished less than 4 years of college. So that's right. We take the 22 and divide by the 174, and that's going to be something close to 0.126. And if we were to interpret that, we would say 12.6% of all Americans 25 years and over are females that have more than 4 years of college, 4 more years of college. Has not completed 4 years of high school. There's no mention of gender here. So gender is an irrelevant variable. So we're focusing only on the educational attainment. Look at that. They say expressed as a simplified fraction. So has not completed. So what you could do is just go through every classification and decide, you know, have these folks have not completed 4 years of high school. So have these folks completed, these folks be included? No, because it says has not completed 4 years. And if these folks took college, then they probably completed high school. So they wouldn't be included. These folks took some college, so they wouldn't be included. These folks took 4 years, so they wouldn't be included. The only group that would be included are these 29 here. And for many of you that said 1/6, you're right on. And if you rounded it, it would be 16.7%. 1/6. Okay, has completed less than 4 years of high school or 4 years of high school only. All right, so I see an or there. So has completed less than 4 years of high school or 4 years of high school only. So you have those two categories. Again, there's no mention of gender here. And so we have to include those that had less than 4 years of high school, the 29 million. We also have to include the 56. But these folks here, they had, they're not in these categories, less than 4 years and 4 years of high school only. So it's just those two, and then you divide by the 174. And I'll always add convert to fraction at the end. So it will give me the simplified version. And then I will do it again. Oops, not that. It's like close to half. All right, the last one has completed 4 years of high school only. Now here's the hardest one of the whole group. Has completed 4 years of high school only, or is a woman. So I'm going to circle all the groupings that we're talking about. Or means one or the other. So they can be a woman, or they can have 4 years of high school only, or both. So we want to select all the women. They're included. And we want to select all of those who have 4 years of high school only. 4 years of high school only, these two. But I'm not going to count the 31 individuals twice. We take 15 plus 25 plus 31 plus 24 plus 22, and then divide by the 174. Over 2/3. Now, because it was an OR probability, what we could do is we could use that addition formula. We're just going to continue to plug along in Chapter 5 on probability. Next, we have mutually exclusive events. We've got complement, and then we have the multiplication rule along with conditional probability. So these are all basic things that you're going to see in an introduction to probability. So we did talk about mutually exclusive before. We talked about it in terms of the sets. And so it's the same idea, but we're going to be talking about it in terms of probabilities. Now, what you'll notice here is you have the set A, which is equal to 1, 2, 3, 4, and 5, because those elements are in there. And you have the set B that's equal to 6, 7, 8, 9, 10. And they have nothing in common. And so what the Venn diagram really should look like, if you look in this region right here, this is the intersection. What's always going to be the case if you have two events are mutually exclusive is that the probability of A and B is 0. And the way that we usually draw that in a Venn diagram would be here is A and here is B, and there's no overlap. But if there was overlap, there would be nothing in that common part in the middle. If two sets look like this, We call them either disjoint or mutually exclusive. And if you're asked to find if two events are mutually exclusive, you have to check one thing, and that is this right here. If you can confirm that the probability of A and B, that is probability of A intersection B, is equal to 0, then you know that those two events are mutually exclusive. You know that they look like this. Now, there is another version of the addition rule. It looks like this. I'm going to write the original addition rule first, but then I'm going to show you what the new formula is if we know the two events are mutually exclusive. So if A and B are mutually exclusive, then that tells us that this guy here, the probability of A and B, is equal to 0. So if the probability of A and B is equal to 0, then it's like it's not even there. And so then we would have the probability of A or B is just equal to the probability of A plus the probability of B. So there are two addition rules here. The one that always works is this one here, but this one also works if the two events are mutually exclusive. So one thing you can ask yourself when you're calculating a probability between two events, you can ask the question, are these two events mutually exclusive? It makes your calculation of the OR probability a little easier. You know, writing these Venn diagrams sometimes can be confusing because we give you so many representations. So for example, one of the ways that I could write this Venn diagram in a different way is with cardinality. And so I look in the intersection and I see there's just one element, and that's the element 5. And so there's just one element in that middle there. When I look over in this region here, there are 4 elements. And when I look over here, there are 5. And then another way we're going to see it, remember that? Number in A equals 5. Number in B equals 6. The number in the intersection is equal to 1. And one last version. If we know that there are a total of 4, 5, 10 elements, then we could write the probability Venn diagram. So you're going to see all different versions of these. You might even see percentages. So this one here would look like this. 1 divided by 10, 0.1. 4 divided by 10, 0.4. And 5 divided by 10, 0.5. Now all of those regions are probabilities. It might make it easier to calculate probability of a union. Sometimes you might even see the Venn diagram, same Venn diagram, with percentages. So you might see 40%, 10%, and 50%. So all of these Venn diagrams, they're just using different numbers, cardinalities, probabilities, percentages, or actual raw elements in there. Okay, so the next formula I want to get involves a complement. And I think we used complements as well in the set section. We did A and A complement. We tried to identify the elements in those sets. We have complements as well with events in probability. So for example, and think about it, the probability of E is our event. The complement would be the probability of not E, anything but E. All the elements, all of the possible outcomes except those in E. So that's what complement means. It means the same thing. We're going to use the superscript C to represent complement. And it turns out that this formula always works, because an element is either in the it's in a set or it's in the complement, one or the other. And all elements in an experiment have to be in one or the other. And so the probabilities will add up to 1. Another way that you would see it is this: the probability of E plus the probability of E complement, that's always equal to 1. And you can see these two are the same if you just add the probability of E algebraically to both sides of the equation. So look for the word not. So with this example here, let's calculate the probability of E, and then let's calculate the probability of E complement. All right, let me write down the set E. So we're kind of going back to sets and looking at sets, but we're going to be doing probabilities, and we'll see how. I'm going to rewrite A, B, C, D, and then I'm going to write E complement. Now the universal set is kind of like the sample space here. So the universal set is A, B, C, D, E, F, G, H. So E complement would be all of those elements in the sample space that are not in E. So A, B, C, and D are in E, but these last elements are not. The number of elements in the sample space is 8. 1, 2, 3, 4, 5, 6, 7, 8. I'm doing set cardinalities now. The number in E is equal to 4. 4 elements, A, B, C, D. The number in F, C, D, E, F, also 4. The number in G is also 4. And the number in H is equal to 2. So just counting up the elements. All right, so the probability of E, remember it's the number of elements in E divided by the number of elements in the sample space, the total number of possible outcomes. We know that the number in E is 4. We know that the number in the sample space is, and so the probability is 4/8, which reduces to 1/2. If you calculate the probability of E complement, you can do it in one of two ways now. You can notice that E complement has 1, 2, 3, 4 elements in it, and the sample space has 8, so that also is 1/2. The other way that you could calculate it is by using this formula. The probability of E complement is 1 minus the probability of E that we just calculated to be 1/2. And 1 minus 1/2 is 1/2. All right, let's take a look through these problems here, because they get at what we talked about before, mutually exclusive sets, events. Also, the complement rule might be in here as well, especially down here in 11 and 12. I think we've already done 11. Find the probability of E complement. List the outcomes in E and F. I think they've done that for us here. Are E and F mutually exclusive? Now, it might not seem intuitive to you, but I'm going to go back to the definition, and I'm going to calculate this. If, when I calculate the probability of E and F, I get 0, then I know that the two events are mutually exclusive. If you calculate the probability of this and that, and you get 0, then those two events would be mutually exclusive. We have E is equal to A, B, C, and D, and we have F is equal to C, D, E, and F. And in the intersection, we have C and D are common. The probability of E and F is equal to 2 over the 8, and that's not equal to 0. So E and F are not mutually exclusive. Okay, next one are the outcomes in F and G. We've got G, we've got F. See them both up there? Are they mutually exclusive? We will test F and G. All right, so we look at all of those elements that are in both F and G. And remember that that means F intersect G. And here's F, and there's G. Have anything in common? C, no, D, no, E, yes, and F. Yeah, so they have E and F in common. So the elements in F intersect G are E and F. The number of elements in F intersect G equals 2. So the probability of F and G is 2 over the 8, which is 1/4. You can clearly see that they would have something in the intersection. They would have E and F in the intersection, so therefore they wouldn't be mutually exclusive. All right, let's look at the multiplication rule now for probabilities. Just like in the addition rule, the reason it's called the addition rule is because addition is used in some way. For the multiplication rule for probabilities, it's as suggested, there's going to be multiplication in there as well. And it's used to calculate the probability of E and F. So the multiplication rule is always the probability of E and F. There are some times when, if the two events are independent, and what independence means is that if you have two events where if knowledge of one does not change the probability of the other, then the two events are independent. So let me give you some examples. Let's say that two events are done in sequence. One is flipping a coin and one is rolling a die. We know that the probability of getting a head is 1/2. And when we flip the coin, we also know that the probability of, okay, let's say E is flip a head. And we know F is kind of let's just say it's roll a 3 when you roll a single die. Now, to answer the question whether these two events, rolling a die and getting a 3, flipping a coin and getting a head, the question that we have to ask to determine if the two events are independent is this. If I flipped the coin and got a head, would that change the probability of getting a 3 when I roll the die? We do know that the probability of rolling a 3 is 1/6. We do know that the probability of flipping a coin and getting a head is 1/2. Does knowledge that I rolled a die and got a 3, or got a 4, or got a 6, but does knowledge what I got on that roll, would that change the probability of getting a head when I flip the coin? Or does the outcome of the die have absolutely no impact on the outcome of the coin toss? And it turns out that these two events are independent. The fact that we would flip a coin and get a head is not going to change the probability of getting a 3 when we roll the die to 1/6. It's still going to be 1/6. You're still going to have a 1 in 6 chance. If one probability is not, if knowledge of the outcome of one of the events does not change the probability of the other, then we would say that the two events are independent. All right, so instead of selecting two cards, the whole conditional probability section, they're going to be two events, and it's useful to think about them occurring in sequence. You do one, then you do the other. So we're going to select two cards, or you can think that you were dealt two cards. Usually the decks are shuffled, and so the cards that you receive is really a random selection of those cards. And let's say that we do it in two different ways. One is with replacement, and the second one is without replacement. And what I mean by this is that we're going to select one card out of the 52 card deck. In the first case, we're going to replace the card back into the deck, reshuffle, and then select our second card. In the second scenario, without replacement, we get the first card and we look at it and then we set it aside. We don't put it back into the deck. We don't replace it. And then we select the second card. Instead of out of 52 cards, we select that second card out of 51 cards because the first card is sitting off to the side. All right, now, whenever we deal with the multiplication rule and conditional probabilities, I'm going to try to draw a tree diagram as much as I can. We introduced those early on, yes, the last time we met, but here's what it would look like. And as my example, we'll look at the probability of selecting, let's say, 2 hearts. And we'll do it in both scenarios. And in the first case, we'll replace the first card back in, draw again. And in the second case, we'll keep the card out and we won't put it back into the deck. So let's do a tree diagram. And let's say it looks like this. We got a heart or not a heart. And that's going to be our first card. Well, we're selecting 2 cards. So the second card, there are 52 cards that we're working with to begin with. So there's still hearts left in the deck after we select the first card, regardless of whether we get a heart or not. So in the second card, we can get a heart or a non-heart. Or it could be the case that we select something other than a heart first, and then when we select the next card, we get a heart or not a heart. All right, so what we're going to do is we're going to put probabilities on all these branches. I told you this was coming last time, but I don't have the graphic for the hearts, but let's write some probabilities on here. Let's say that from a 52 card deck, we're going to select one card, our first card. What's the probability that it's a heart? It looks like Jay's right on top of that one. That is correct. 13 out of 15. Right, there are 13 hearts and 52 cards. So we're going to write the probability 13 over 52 on that branch. Let's go down to the lower branch. What's the probability of getting something that's not a heart? We're selecting from 52 cards, 13 hearts. How many non-hearts? 39. We have the 13 clubs, 13 spades, and 13 diamonds. Okay, let's say that we select the card and it's the 3 of spades. We note that that card is the 3 of spades, and we continue on with the experiment. Now, the first experiment is that we're going to do this with replacement. So we're going to take that 3 of spades and we're going to put it back into the deck. And then we're going to select again. Given that the 52 cards are still back together, what's the probability of getting a heart when we select the next card, the second card? Something has already happened. But we're still selecting from 52 cards. We still have the full deck. There's still 13 hearts in there. There's still 39 non-hearts in there. And because we're replacing the original card back in, these probabilities do not change. 13 out of 52. Of course, those also reduce, right? 1/4, 3/4. 1/4 of the cards are hearts. 3/4 of them are not hearts. Now, does knowledge that we have the 2 of spades, that was our first card, remember that? Or the 3 of spades? I took that out here. I recorded it. It was 3 of spades. Does my knowledge that we got that 3 of spades, does it change the probability of getting a heart on the next draw? We know that it's not a heart. Is this probability different than this one? Does knowledge that we have that 3 of spades, does that change the probability of getting a heart on the second card? And the answer is no, it does not. The probabilities are the same. So we would say that these two events are independent. All right, let's go to the second example where we have 2 cards, first and the second, but we're going to have the scenario without replacement. So after we look at that 2 of spades or that 3 of spades that we've drawn out, whatever card it is, we're not going to stick it back in the deck. So the question is, does it then change the probability of getting a heart in our second draw if we have knowledge of the first card? Now, the first part of this looks the same. What's the probability of getting a heart? 13 out of 52. What's the probability of getting something else? 39 out of 50. So the first probabilities are the same. Now, the second branching, this is where things change. If we're coming up this branch, that means that the first card that we selected was a heart. So maybe it was the 7 of hearts, let's say. Let's say that we know that that's our first card, and now it's sitting on the table. We're not replacing it into the deck. So just envision that. How many cards remain in the deck if the 7 of hearts is sitting on the table? You following? Okay, good. 51, because it was 52, and then we took out the 7, so it's sitting on the table. So in our next draw, we're not selecting from 51, or from 52, we're selecting from 51 instead. Okay, now keep that in mind. We're going to be selecting from 51 cards. All right, now remember, it's the 7 of hearts that's sitting on the table. We know what it is. So that means there's 1 fewer heart in the deck, in addition to being 1 fewer card in the deck. So what's the probability of getting a heart on the next draw? There used to be 13 hearts, but the 7 of hearts was first drawn. So now there's only 12 hearts. And there's only 51 cards. So the probability of getting a heart on the second draw is 12 over 51. Then what's the probability of getting something else on the second draw? 39, because there's still 39 non-hearts in the deck, because the first card we selected was a 7 of hearts. In the next one, let's assume we're coming down here. And if we're coming down here, that means the first card that we selected was not a heart. So let's say it's the 2 of spades. Now, instead of the 7 of hearts sitting on the table, the 2 of spades is sitting on the table. Well, since a card is sitting on the table, when we select our second card, we're only going to be selecting from 51 cards. How many of them are hearts? If we're down here, and we know that the first card we selected was the 2 of spades and it's sitting on the table, what's the probability of getting a heart? You are correct. 13 out of 51. all 13 hearts are still there because the card we selected out was the 2 of spades. But there is one fewer non-heart because the 2 of spades is sitting on the table. All right, so this is this whole idea of replacement or not non-replacement. And let me ask the question again. Does knowledge of the card that we have, let's say we knew we had 7 of hearts and the 2 of spades, does that change the probability of getting a heart on the next draw? If we knew we had a 7 of hearts versus a 2 of spades, then the probability of getting a heart on the next draw would be different. These two numbers here are not the same. And if that happens, we say that these two events, selecting a card on the first draw, selecting a heart on the second draw, are not independent. So that's the idea of independence. And students get it confused with mutual exclusivity or mutually exclusive. They're not the same thing. So you will be doing, well, I'll give you some formulas to decide if two events are independent or not. All right, I have to, well, now I'll just give you the multiplication rule because that's where we started. If you have two events that are independent, then the probability of E and F, and the multiplication rule is related to the probability of E and F, also known as E intersect F, is equal to the probability of E times the probability of F. Multiplication rule. Let me give you another example. Maybe one that involves two different games of chance. And I think we've had this example already. Let's say we're going to flip a coin and roll a die. And our events are flipping a head, tail, and let's say that for the roll of the die, we're going to get a 3 or not a 3. Now to make this kind of more concrete, I'm actually going to write down all the outcomes that you can possibly come up with in this experiment. The experiment is that we're going to flip one coin and roll one die. And here are the outcomes. You can get a head and a 1, a head and a 2, a head and a 3, a head and a 4, a head and a 5, or a head and a 6. You can get a tail and a 1, a tail and a 2, tail and a 3, and so on. But when you flip one coin and roll one die, these are the 12 outcomes. You can count them there. 2 outcomes on the coin toss, 6 outcomes on the die flip or die roll, so that equals 12. That's a multiplication rule. So what we're interested with the multiplication rule, and we've already established that these two events are independent, then this should apply. This formula should apply. But we can also calculate it. Let's say we wanted to calculate the probability that we get a head and we roll a 3. In my notation, that would look like this. Probability of head and 3. What's the probability of getting a head and a 3? 12 outcomes? How many of those outcomes are H3s? Yeah, just one. So the probability is 1/12. But what's the probability of getting a head if you flip a coin? Thank you. 1/2. What's the probability of getting a 3 if you roll a die? 1/6. So if you take this number and multiply it by this number, 1/2 times 1/6 is equal to the 1/12. So you can see it here with this concrete example why it works. If you can construct a tree diagram, and what it requires is it requires you to set it up, and it requires you to put probabilities on the branches. If you can do that, and you will have to do this in a lot of our examples, then it's going to make your probabilities much easier to calculate. So here's how the tree diagram works. You put the probability of a head on the branch leading to the head. You put the probability of getting a 3 on the branch leading to the 3, like this. Put probabilities on all the branches. Then, if you wanted to calculate the probability of head and 3, just follow along the branches, head and 3, and multiply. 1/2 times 1/6, and you're going to get the 1/12. This works whether or not the two events are independent or not. So here's a generic tree diagram, And I want to introduce now conditional probabilities. Conditional probabilities are probabilities of an event occurring given that something else has occurred. So there's a condition that we put on the probability we're calculating. Something else has occurred. We're shrinking the bigger sample size. But you can see it in a tree diagram, so that's what I'm going to draw. So let's say the two events that are going in sequence, the two outcomes are A and B on the first event that occurs. And then the second thing that can happen is either C or D can occur. Now, this probability here, the number that we put on this branch, is the probability of A. Nothing has occurred beforehand. So this is not a conditional probability. This is just the probability of A. And this one down here is the probability of B. Now, all of the probabilities that come next, something has already happened. A die may have been rolled, a first card was selected from a deck, something happened to begin with. So all of these probabilities are known as conditional probabilities. For example, if we're going to calculate the probability of C, this one here, yeah, it's the probability of C because we're going to C, but here's where the conditional probability comes in. A has already occurred. And the way that we say that A has already occurred is we write a vertical line with the letter A. And then we're going to say the probability that C occurs given that A has already occurred. The probability of C given A. And this is a conditional probability. All of these are conditional probabilities. They all look a little bit different. As we come down here, this is the probability of D given that A has already occurred. Okay, what's this conditional probability? The probability of what? If you look at the pattern, what event goes in here? In this one, instead of A having already occurred, B will have occurred down here. Okay, good. And since we're going to C, it's the probability of C given that B has already occurred. I'm going to give you lots of examples so you can, calculate some of these conditional probabilities. But the first thing I have to do is give you the formula. And this one is the probability of D given B has occurred. All right, so if you can understand this idea, then you can understand this formula I'm about to give you. I already mentioned that if we want to calculate a probability of two things happening, we just multiply the probabilities on the branches. Well, if we have A first and then C, what we would be calculating is the probability of A and C. A and C. If we go down this path, it would be the probability of A and D. If we go down this path, it's the probability of B and C, B and D. And if you want the probability of A and C, just multiply these probabilities. The probability of A times the probability of C given A, like this. And this is known as the general multiplication rule. It works whether or not the two events are independent or not. This is known as the general multiplication rule. Now, if you do a little bit of algebra and you divide both sides by P of A, you have another formula that we use quite regularly. Here, the P of A's will cancel. So you'll have the probability of C given A is equal to, and over here, you're going to have a fraction. The probability of A and C divided by the probability of A. And this is known as the conditional probability formula. Okay, let's go ahead and look at some examples to see how this is going to work. You have lots of formulas thrown at you today, so all of this might just seem really Greek to you at this point, but as you practice these more, it'll start to make sense. Look for connections, look for patterns, draw the tree diagram in every case if you can. Let's look at example 1. So you can get a sense of what the verbiage would look like for conditional probabilities. Example 1, the probability that a randomly chosen student plays in the band is, 1 over 50. The probability that a randomly chosen student sings in the choir and plays in the band is 1 over 200. What is the probability that a randomly chosen student sings in the choir, given that the student plays in the band? All right, let me set this one up for you, and then I'll give you another one where you can try it yourself. All right, so let's say B is the event that a student plays in the band. And let's say C is the event that the student plays in the choir. So those are two events. That's what they gave us the probability. The probability that a random chosen student plays in the band is 1/50. And I got that from right here in the problem. The probability that a randomly selected student sings in the choir and plays in the band is 1/200. So that's what it would look like. We're converting those words into our mathematical probability symbols. And then they ask you the probability. What is the probability that a randomly chosen student sings in the choir, given, see the given that's where you put in the vertical line, given that the student plays in the band. So this is the probability that they want you to find there. They've given you everything that you need because this formula works for any two events. And we don't have A in our problem, but we do have B, so I'm going to change all these A's to B's. And there's the formula. The probability of C given B is equal to the probability of B and C divided by the probability of B. This is a formula. So, and they gave us these two numbers, right? So you take 1/200, that's the top number, and then 1/50, that's the bottom number. And the only thing left to do now is to simplify it with your calculator. And so the probability is 0.25 or 1/4. And so they, one of the tools that you're going to have to do these probability problems are all of the formulas. So let's summarize. The probability of an event is equal to the number of ways that the event can occur divided by the number of outcomes in the sample space. That was the basic definition of probability. It could also be the probability that event E occurs divided by the probability that event S occurs. And there are a couple of other definitions. Sometimes just this definition will work. We have the addition rule. There's two versions. It works for the probability of E or F, and that's equal to the probability of E plus the probability of F minus the probability of E and F. There's one other version of this, but it's almost never used because it only works in a very narrow setting where E and F are mutually exclusive. Addition rule, complement rule, the probability of E complement equals 1 minus the probability of E. So if they ask you to find the probability that not something, just take 1 minus the probability of that something. The multiplication rule for the probability of E and F is equal to the probability of E times the probability of F given that E has already occurred. That's the general power rule, or product rule, or the probability of E and F is equal to the probability of E times the probability of F. You don't need that given part, but it must be the case that E and F are independent. And the last one is the conditional probability rule. This is the one that we use with tree diagrams. I guess we can also use this one up here with tree diagrams, but it's the probability of E given F. That's the probability of E, probability of E and F, divided by the probability of F. All right, so there they all are, all the formulas that you're going to need for the section on probability, but there are ways that you can calculate probabilities where you won't use these formulas. So don't assume that you're going to be using these formulas every time, but they are one tool that you have to do a lot of problems.